Okay, so let's start with our next part. That is the part 2 or lecture 2 in the first week. And this is definitely the real introduction to statistical learning. What we have is, we like to have some, notions on supervised learning and unsupervised learning. We saw little definition and we'll elaborate a little more. And then we'll go for an overview on understanding statistical learning. So that is definitely introduction. So, and see, while we will, talk about, this statistical learning. So there are various topics that you might not understand right now. But I believe that if you have some background that I clarified in the first part, so eventually as we go forward, little by little, gradually, you will be grasping the concepts and ideas, and you can apply on various problems. But in the beginning, so especially in introduction to statistical learning, it's an overview. So many topics might be little harder. But then we will study maybe from next week. We'll be starting on linear regressions. So, and I believe that you have some idea on that, especially in hypothesis, inference, and testing. So then we will go forward. Okay. So let's see, and we'll also see some assessing modeling accuracy. So, but maybe this part we can't finish because of time limit. So perhaps in the next week we'll be starting from here, but in today, now in this part, we'll be trying to cover up with the first two topics. Okay. So let's talk about supervised learning. So in supervised learning, then we have some measurement, right? So the measurement is y, and this measurement y, we also called dependent variable or response variable or target variable or simply target response, this kind. And we have some inputs. The inputs may be p number of inputs. These p predictors. We say predictor measurement. And we also say this is regressors, covariate features or independent variables, because this is a dependent variable. So that means this y depends on this number of inputs. So this number of inputs is independent variables, and this is dependent variable or response or target. So that means if this is our inputs, so this is our response, or this is our target. So that's it. So it's very simple. Okay. So how about turning off the video right now? Based on that, we have two sorts of problem. One is a regression problem, and in regression problem, y, that means this one is basically quantitative. So it might be price of some product or maybe blood pressure. So how is the blood pressure concept? For example, maybe the blood pressure y depends on some physiological conditions, maybe some x1, x2, and something, right? So that's it. And then you also have the classification problem. If this y takes some values in a finite, from finite values, so then we say that this regression problem become actually classification problem. For example, a person or a patient survive or die, or maybe as we saw an example that we have some handwritten digits. So this digit identification, so which digit it is 0, 1, 2, and up to 9. So that's also a classification problem. Or let's say we collect some sample from our human body and organ, and then we see that this specific tissue sample is basically cancer or non-cancer or something. Or maybe this is cancer, but what kind of cancer it is? It is stage 1, stage 2, stage 3, so that kind of thing. So that is called classification problem. And all we do based on some training data. So training data means we have some observations. Observations is basically examples or instances of this measurement. We have some known measurement. We know that if our x is this, then we know this is our y, and maybe another observation we know, and then eventually based on that training data we can design our model so that in the future we can predict. Okay, so see, here are some observations. See, this is definitely only one input. So that is, for example, that the education, how many years of education someone has, and based on that, what is the income. So this is one observation. this is another observation, this is another observation. Here are total 30 observations. We just do a plot that is called some sort of scatter plot, right? And definitely this is only, we have it's only one dimension or only one features or one independent variable, that is years of education, and we have this one dependent variable or response. So this is y, and this is only because on only one feature, so we say x. Okay, so but in general, if we write to have a generalized form, so how it looks like. So definitely there we have maybe let's say generally we have n observation. Okay, so we think about like this, that generally we have n observation or n training data, right? So we can say that let's say this I equal 1, 2, n up to n. So this is our number of observation, n observation. Okay, and how many features, let's say if you go back here, that we saw that how many, let's say how many predictor measurement or how many features, let's say we have p number of features. Okay, so if we have p number of features, so let's say the p number of features mean, let's say j is 1, 2, and up to p. So if so, then what is our how we can notify, how we can denote the training data. So that's our idea. So let's say then we can say that, let's say x I z. Okay, so this is a very simple things, x I z. So let x I z represent the value of z predictor or input or observation for observation I. So for example here that I'm writing here, so this one, so let's say this is which observation, we have nth observation, let's say we are talking about ith observation, so we can write in this way, x ith observation, for ith observation which input variable we are talking about, let's say we are talking about j, so we can write this in this simple way. So then our training data would be like something like this one, let's say x1 y1, so this is one training data and one observation. So let's say this is x2 y2, this is the second observation, something this one, for example, let's say this one is the our first observation. So this is the x and this is the y, right? So this is the y and this is the x, because we have only one predictors, that means one input, so that's why here is simply x1 mean only x. Anyway, so x1, x2, and in this way we have xn and yn, this n pairs of data. So this is our training data. But definitely this one x, let's say this x1 or x2, let's say any xi basically a vector, and this is actually for the ith observation, and the input number is 1. The ith observation, let's say our ith observation, then the input variable or feature number 2. So in this way our ith observation and feature number is p. So this is how we write. Okay, so this is a very simple notation, so we need to follow. And sometimes we write in this form. So this xi basically are vectors of this p number of predictors, or we can say this is the p number of our independent inputs. Okay, so this is how. So on the basis of the training data, then we would like to accurately predict some unseen test cases we don't see, and then we can predict. So for the known data, from the known data we first train the model, build the model, and then we can see. And on the basis of this training data, we also want to understand which input affects the outcome and how, right? I mean, if we have multiple inputs, for example, like this one, if we have multiple inputs, we like to see that which input affects this y and how, or how much. So everything we try to understand. And also we like to see that the predictions that we did, that what is the quality of this prediction. This prediction is good or not good, or we like to have some idea on inferences. Inference means that the relationship between one input variable to the other input variables, or sorry, every input variable to to the output variable. So that is the way. So we'll see all of these things little by little more later on. Now see this supervised learning, how this name came from, the supervised learning. Supervised learning, actually the name came, from something about like that. Let's say there is a child, and so the child is going to, let's say, school and kindergarten or somewhere, and there is a teacher. The teachers teaches the students, right? Let's say there is some toy in a house, and then see that, okay, this is the house. Let's say there are some house and there's some bikes or something. So the teaches the kid or baby, says, hey, this is the the house. So house may be this kind of shape and this kind, and this is the bike. Now the child, the baby, he basically want to see, observe, okay, the house looks like this one and bike looks like this one, right? So this is actually a training. Now later on, if you given some new house and new bike, he can understand that this is the bike and this is the house. So this is the idea of supervised learning. So you basically supervised, and then the model or the kids actually learn. Now how about the unsupervised learning? In case of unsupervised learning, we don't say that, hey, this is the house. Rather, let's say we put together, okay? Let's say somehow there are some house, there are some bikes, we just put together. And then maybe the baby, he can see, okay, this looks like similar, so this is one group, maybe house. Even we don't know what is the name of that. Maybe this is one group, and this is, the bike looks like round shape and those kind of things. This is maybe another group. So at least that kind of, classification, or clustering, clustering actually, not classification, clustering that can be performed, or grouped can be performed. So that is the idea of unsupervised learning, okay? So in unsupervised learning, then there is no outcome variable, just a set of features. We just have system of features, right? For example, the house features and the bike features, that kind of things. And objective is more fuzzy, so that means there is no very directions that what we want to do. So sometimes it is difficult to know what we are doing, okay? But different from supervised learnings, it can be useful, especially in many cases. For example, web data, or in many data is actually this unlabeled data. And for unlabeled data, first we need to have some kind of grouping, and this is some sort of pre-processing, and then we can use that data for maybe for supervised learning or something. Okay, so that's pretty okay. So lastly, let's we talk about this one, that what is statistical learning versus machine learning idea. So machine learning basically is a subfield of AI, right? There are some other things other than machine learning. There are many other soft computing techniques like generic algorithm, fuzzy logics, those kind of things. But statistical learning is coming from a subfield of statistics itself. Definitely there is much overlap, and both focus on supervised and unsupervised problems. But machine learning generally has a greater emphasis on large scale data, and it also try to focus on the prediction accuracy. Okay, so it try to see the result, and it try to increase the prediction accuracy. The purpose is important, and statistics learning so more focus on the models, okay, and the interpretations, that why and how this model actually working. So precision and uncertainty is basically dealt in the statistical learning, whereas machine learning, their target is prediction accuracy. Okay, and definitely that machine learning is nowadays is more about the marketing terminology. See this one, that here in front of us, there are three figures, and this is basically sales figure. This says that you spend some money for TV advertisement and you look the sales. Okay, so these are different data or different observation, that when we spend for example, so let's say $100,000, then what would be the sales or something. Or if you spend this much of $200 or something, and then what is the sales. So this is that the money or expenditure that we spend for TV advertisement, and what is the sales. Okay, and this one, that if we have the radio media that we are spending some money for the radio advertisement, and then what would be sales. Okay, so these are some data definitely, and this is for the newspaper cases. And you see that for example this TV, see in these cases maybe this all of this data can be generally represented by this blue line, right? Maybe some sort of representative line. And similarly for this one is this blue line can be represented by this line. So this somehow we say this is a linear feed because the line itself is basically a linear line and it represents a linear relationship between radio and cells. Definitely the real data, this our observed data is not exactly this line doesn't fit all of this data, but somehow it's a trend, right? We see the trend. And for the newspaper is this kind of things. This is if we like to find out the relationship in a linear manner, so maybe this linear line may be the case. So but for these two cases the relationship is more stronger than this one. This is more about less related or loose relationships here we see. So so this is this blue, actually we say the linear regression line that fits separately to each, right? So now, so how about, can we predict the cells using these three plots? Perhaps it might be difficult, but how about if we jointly consider these three figures? So that means the cells perhaps might be predicted when we have a model like a function that okay, so ultimately cells is a function of the money that we spend for the advertisement in TV, radio, and newspaper together. So this F is basically a function, or we say model. Okay, so what kind of function this is, that is a different thing, so we will see these things later on. So here cells is basically a response or target that we wish to predict. So this is the Y actually, right? So this is represented as Y. Now in the TV features, maybe this can be considered as an X1, and likewise the radio, maybe this input maybe or predictors maybe X2, and similarly there's another is X3. So similarly that as we wrote, this might be captured with this notation that X is basically a column vectors like X1, X2, and X3. So finally we can write our model is like this one. You see the Y is basically function of X, and there is some little error term. This may be measurement error or maybe any kind of discrepancy that we might have. So this is the things. Now in essentially the idea in statistics learning is that that we will have to estimate this F. Okay, so and how we can do that, those are the approaches that's called statistical learning. Okay, so I'm again turning off. So now the questions comes that what we can do with this this F. So definitely first of all we can at any new points, if we have some let's say at a particular new values, let's say x equal x, at x we can actually predict the values of y because we know the relationship, right? So we can understand also that which components are more important in explaining y. Okay, for example, that this x is basically x1, x2, and up to xp there might be p number of predictors, and we can see that which features, this one or this one, have more important influence on y. So which one is relevant, which one is more not relevant, something like that. For example, so if we think about the income of a person or of individuals, maybe his seniority somehow play the role, and how many years of education this person has, it also might have impact. But maybe his or her marital status doesn't matter, right? So that is the idea. So depending on the complexity of the app, that what kind of function or model it is, we maybe understand that how each component of this J affects. So this is an idea. This is the things of the interpretations or inference kind of things. If your model is complicated, maybe we don't know that how each components affect this one. And if our model is simpler, maybe we know, right? So it depends on. Okay, so is there any ideal a function? That what is the ideal functions? So or in say that what is a good value for this function at at any selected value of x. For example, let's say here is only, let's say x equal 4. Okay, we are talking about, let's say, only one input. Okay, we are not talking about the vector input, only one input we have. And let's say this input, generally, let's say x, and for this x, let's say we have a very particular, value x equal 4. Okay, very particular value x equal 4. So like this one. So like this one. Okay, I'll write something just, okay. So at just, at x equal a particular value x, let's say here, 4. At 4, what is the good value? You see, there are many data points, right? This is our observation. And you know how many data points are here? It is actually maybe 2000 data points are there. And at very particular x, let's say x equal 4, at 4, you see there are many values, right, in observation. But which value is, we will be considering? At what is the value of y would be? What is the good value, right? Now, so that means we have, x equal 4. Now maybe the good value, one good value we see. So you just consider all of these possible, things, right? At x equal 4, these are the, all the, so values might be from here to here, right? Any value can be taken. This is the value of y. So this is the value of y. At here is the thing. Now at a very particular, point, let's say x equal 4, maybe there are, this is the range of the values of from here to here. So which value is the good value? Now that is the idea. Now one good value is one good function is like this one, that you have x equal 4. So given that x equal 4, then the y, then how about this one, that if we just, take average value of this, all of this y, we know that how many y's are there, and then if we take the average of that at these values, so maybe that is a good value, and actually this is indeed the value. So x equal 4, so given that x equal 4, so you will just, you just, measure the expected value or average. This is actually mean the average value. You just take the average value, and this is the good values for, f of x. We are trying to calculate that f of x, right? If x equal x, if x is 4, what is the good value? So the good value is actually at this point, this conditional, expected values, that at x equal 4, you just calculate the expected values of y. So that means you just take average of all of this y, and this value is your good value or expected value. Okay. Now ultimately, if you just, consider in this way, at each x, if you just, at each x, let's say x 4 and 5 and at every possible points, then you just come up with this red line. Okay. So this red line is called the regression function. Okay. Regression function or regression line. Regression function. Let's say regression function. Okay. Now this regression function definitely is also defined for the vector. So it's not only just, one input variable. If you have, something like x equal, let's say x1, x2, and x3, definitely at particular, values x1, x2, and x3. So we'll have to write accordingly. So how is that? That let's say at x1 equal x, at x2 equal to x2, and x3 equal to x, what are the, different values of y, and then we take expected value or average value of that one. So that become the good values for that one. Now you probably, I don't know, you understand it or not, but think about that. Let's say we have some, let's say we have, let's say 2 dimension, because this is a 3-dimensional things, right? x1, x2, and x3. Now think about the table, the 2-dimensional table. Let's say x1 in 1 dimension and x2 is another dimension, and let's say the very vertical things is our y value or the response value. Okay, so this fx value. Now what we have then in this plane, so you can come up with on the plane any points on the plane x1 and x2 plane. You can take any point, and for this point you have some certain values, in y, right, in the response. So you just take the average of all of these values, so you will get that at that particular points you get it. I mean, definitely, I mean, here is 3-dimension, but I explained for 2-dimensional cases for understanding. So that's how we can perceive and realize for a multi-dimensional, 3-dimensional, 4-dimensional cases, or for number of predictors. That's the things. So, and it is also, the very interesting thing is, it is also the ideal, this is also the optimal predictors. Now what it means is optimal predictor. Think about, like this, that, let's say, by the way, I mean, we have a very little notation that, let's say this is our, true function, that let's say this is our true, relationship, between x and y. And definitely we know that there is some error term. So this f, we like to estimate, right? We like to, determine. So this is the true function, and then, if we just represent the estimated function, we sometimes write this one like this one, the f small hat. So similarly, using the estimated function, if you like to, find out the y value, so this will be the predicted value of y, or the estimated output or predicted output. So this is a simple notational things, okay? So then now let's see that when we, we have some, particular x or something, we have, let's say, any function. This is generally, any function, let's say this function that we just, determine, like, at any given values, let's say x equal to x4, or let's say x equal x1, and then we like to see the value of y and its expected values of that particular point, right? So this is that we are saying this is the optimal function. Now what it means, you can have, let's say, any other function other than fx, let's say any other function, gx, okay? And let's say at a very particular, x, maybe given that x equal a very particular xx, you just take any functions, and then this is your the response variable. If you just take, subtraction of that at this particular point, let's say y minus g of x, and if you just take, square of that, and then given that x equal, at a particular point x, and if you take the average values of that, so what's happening, this one, whatever, value you take, that, if you just take f of x, this f of will be the minimum one. So that why we're taking this square and this one. This is basically, we will understand this a little later, but this is basically error, right? This is, let's say at a particular x, the value of y is y, and if we just, calculate the function, this f of x, and then, or let's say g of x, so then you just take subtraction of that. So this is basically becomes your error, right? This error. What is the difference between this value and if you calculated values or estimated values? And this is error. So sometimes, this error we represent, by square of that, okay? And given that x equal to particular values of x. Now what we wanted to have, this expectation, this is, one particular values, but if we, take average of all the values at that particular point, so this will be your average value. Now this average value, if you just take any other function, and if you take, this function, like this one, that if you just, take the average of that one, this kind of, function that we calculated here. So this function, this regression function line I'm talking about, this function, this will, provide you the lowest, lowest error. So that's why it is optimal, function. So okay, right now we don't need to understand these things much more. Then, I like to say something, another, things. So that is here. So ultimately you see that our relation, was like this one, y equal f of x plus this sometimes, some error term. Now definitely this error is basically, a random error, right? You don't know. So generally when you assume like this kind of, function, f of x plus, f of x plus epsilon. So this one I'm talking, actually I wrote this one, if you saw that y equal to f of x plus epsilon, this one. So y equal f of x plus epsilon, this epsilon is basically your random error. Now sometimes this will be some, plus, and sometimes this will be minus. So on an average, this will give you, if you take the average of all of this one under a given observation, that it will be zero mean. Okay. So that means average value will be 0. Okay. So let's go back here. So average will be 0, that we understand. But definitely, so how is this one? Then epsilon is actually y minus f of x. This is actually your error term, right? So this error is basically, we can't avoid this error. I mean, even though your model is very great, but definitely you will, let's say this f(x) ideal and whatever, but definitely by definition, because this is true value, true function, and then by definition this error will be there. So that means this error, that is the difference from y minus f of x, we can't avoid this term, right? Because this y itself, when you go to a particular values at x and you calculate the y itself has a distribution because of this error term. Okay, but let's see, this is our y, and this is our, let's say, a predicted value. So this is actually the error term, and let's say, so this is the error term. And if you just calculate the expected values of this error term, and then if you just expand it, this simply statistics, if you just take the square of that one, let's say you just take square of that one, and then, I mean, error, if you take the error and the square error, it is better to take a square error. I don't know you know it or not, but I will explain maybe on some time later on. So if you just explain it, if you just expand it, that let's say this y is basically your f of x plus this epsilon, right? This y is basically f of x plus epsilon, and then you have this estimated one, and then you have this square, and then you take expected values of that, and so then you need to just expand that, and you will get, if you just expand this one, then you will have this one. Okay, now how these terms comes out, these terms, it is very easy. From this line to this line, how it comes, you see the f of x, we can write minus f of, this is the estimated one, so definitely we can consider that this one is the square, and then plus 2 of f of x, and then this one, and then you have multiplied by epsilon, and then plus multiplied by epsilon square, right? Epsilon and epsilon, and then you have expected value of all over, right? So if you just take expected value, because it's all summation, so you can take expected value over here. So expected value of your f of x minus this one, so this is plus, now see this one. So here, let's say for this time being, we can think that for a very particular x, so this is fixed and this is also fixed, so this is basically become 2, because this is constant, so f of x and then expected values of epsilon. Okay, now plus expected value of epsilon square. So this is how it is. Now see, what is the mean values of this one? We already told that the average values of this epsilon or the error term is 0, so this is basically become 0. And how is this one? So this is basically, that this formula, this one, that expected values of x square minus expected value of x, this square basically is equal to variance of x, these things, because the mean value is 0, so that means this is actually the variance of epsilon square. So we can write in this manner. So this is variance of your error term, and this is your simply the true function difference or subtracted by the estimated function. So this error actually we can't reduce, we can't avoid this error, because this is coming from the randomness and this is coming from the error terms. But this one we can reduce if we have a better model, so that means this one will be closely approximated by this one. So that's why we say this is reducible error and this is irreducible error. Okay, so typically so how do we estimate then, how to estimate this f? So see, so it is okay. So let's say we have let's say these data points here. So generally at a very particular location, let's say x equal 4, there are actually we have few data points, we don't have actually many data points. See this example here, there are some data and observation or training, whatever we say, at a very particular x, let's say x equal 4. You see there are, this black circle is basically our observation. Now here we don't find any data points, or maybe very minimum data points. So that means the idea of this one, that at very particular x we just take the average of y, it doesn't work, right? So what we can do? So still, we can work out so that we try to lose our definition, relax the definition. Now what we can do is, not only just at this location, maybe what we can do, and maybe nearby location, maybe 4 and a little bit more, you go rightward and a little bit go leftward. So within this region, okay, within this region, this is the neighborhood, we can say, okay, the nearest neighbor. Maybe you just go a little bit, right side and a little bit, left side. And we are talking about only one dimension. This is only one dimension, x, that is x, only one dimension, okay. So the idea is you now have, some other, points, right? Some other data. Now we will just, so from here to here, these values. So we just take all the, sum up all the values and then make the average of that, right? So this is, called, neighborhood or nearest neighbor, averaging. So, and the definition, you see it was x equal exactly x, but now x is basically coming from all the points that coming from the nearest neighbor. So this is how we represent n of x, because this is the how we do. So where this n of x is some neighborhood of x. Now this seems very interesting, and it really works very good and very powerful. But the problems happens is, that, it generally works, if we have, less number of, predictors. That means less number of features or less number of dimensions, okay? And also we need large, number of data points, large number of n. So if our data points, if our this, dimension become more than, 4 or more, or maybe more than 4, it doesn't work well. Also, if our data points is number of less, it doesn't work well. And we'll see shortly how. So there are, this is basically this nearest neighbor, that averaging that we do, it is basically one version of there are many techniques. This is somehow called smoothing technique. There are other smoothing technique called kernel, splining method that we will see later on. So nearest neighbor method, basically, as I told, it performs very bad when p is large, and this is, we say, this is coming from the reason of, we say, curse of dimensionality, that if the dimension increases, the problems happen. So let's see, this figure that we are trying to, let's say these are some of our data points, okay. So these data points, we see that, there is one information that we need to say, that we are saying that, we need to get a reasonable fraction of the n values. Let's say we have, 100 data points. Now, to work this nearest neighbor well, at least 10% of the data you need to consider to perform, this, nearest neighbor operation. For example, here, let's say you have total 100 data points. At least within this, area, you need to have at least 10%, of our whole data points. So let's say if you have 100, so at least 10 data points you will have to have within this region. Otherwise, it is not good fit. So the problems then happen when you basically, let's say we think about, these data points, and let's say we think, let's say one dimension. Let's only this dimension, this x1 dimension, and this is, at this local point that we are trying to, find out the average. So you go and you just consider, neighborhood operation. So use the neighborhood averaging. So you go little rightward and little leftward of that, and you got the very small, this area, this width. Okay, within this width, you got some data points, and then you make, take the values of y from this one, and then you make the average. But then let's say we now go for the two-dimensional cases. Okay, now these two-dimensional cases. Now, why we find this, for one-dimensional cases, why we took this one? Because it was enough to get the 10% data with this data point. But now you go to the second dimension. Now, when you go to the second dimension, so now things becomes, to get the 10% data points over this entire plane, you basically need a larger radius. Now, within this radius, so in one dimension, you had a small radius. But now when you got the two dimension, so to capture the 10% data points, you basically need to consider a larger radius. Okay, so So that's okay in two-dimensional cases. So the fraction, there is an experimental graph for performance analysis. Here we can see, let's say this is a fraction of the volume of data, so that is, let's say 10% data, 20% data, 30% something, and let's say this is the radius, that how much radius we need to consider to get the 10% or 20% or 30% of your data. Now let's say when this we have only one dimension, so in that case 10% data is we are getting with a very small radius. So, and this was that small radius, but let's say this variable now become 5. Okay, so that is a independent variable or predictor, number of predictors become 5, and for this case you see, to get the 10% of your data you need almost how to say that 70%, or that is the 0.7 or 0.1, that kind of radius. So that means if you take the 0.7 radius, you go up to here and up to here, so it is almost the entire data. So if it is almost the entire data, it is not neighborhood anymore. It is not confined with our local considerations, right? So you see, if you go back here, this was still we are considering the local averaging. So why local averaging? We believe that at x equal 4 and at x equal slightly more or slightly less, the value of y should be almost similar. But if you consider at 6 or 7, definitely we can't guarantee, because it is not within the local region anymore. So that's the curse of dimensionality or dimensionality problem. So this is that we will be learning in these courses. And so ultimately what? I mean, there are problems that you basically need to reduce the number of dimensions. There are some certain cases that is called dimension reductions. Perhaps we will see that how to do that. So then how we can do that? What is our model? So then you come the parametric and structured model. We need to do some parametric and structured model. So in parametric, let's say we consider linear model, an example of parametric model. So there, we can consider that our function, maybe represented, maybe this is one of the, way that how we can, represent this parametric, function. The parametric function means, let's say we have, we have certain number of predictors, maybe x1 and x2 and up to xp. Now what we can do, we can just take linear combinations of that one. So that means our function or model, this is a linear model, and that is parameterized by, let's say if we have p number of predictors, then we have p plus 1 parameters. The very first one is beta naught, and then beta 1, and then beta 2, and then beta p. So you just consider the predictor p weighted by bp, the parameter p, and let's say you have predictor 2, and then parameterized or multiplied by or weighted by parameter beta 2, and this is parameter by beta 1, and this one is basically a intercept term. The very the first term is beta naught. So this is actually this sorts of linear model, we have p plus 1 parameters. Now if somehow we can estimate these values, that is beta naught to bp, so we can then estimate this one. So this is the idea. Okay, so that means think about this, that let's say we had a function, so this function we can somehow, let's say we model this function maybe with a linear model, and this model can be considered like we have, let's say, parameter beta 1 and x1, beta 2, x2, and then in this way parameter beta n and xp, because we have p number of variables. So this is so we okay, it seems there was some disturbance in this system setup, but I hope that we didn't miss most of the things. So anyway, so we estimate these parameters. Now if we can estimate these parameters, like an estimation of this one, we can represent, let's say, this beta, and then in this one, this beta naught, and then hat, and beta naught 1 hat, beta 2 hat, something like this one. Then and by using training data, we find out this, we estimate these values, and then we can find out these other values. Definitely there's any model, this linear model, is not never enough and never correct exactly, but it is a good enough, and it has good interpretable approximation to the unknown true function. So in this way, if we just try to estimate this true function in this manner, in many cases it becomes a good approximation. So for examples here, see linear models. Here we have, let's say, two parameters, let's say, and because it is an only one dimension or one variable, you can say the predictor, one predictor, so you have two parameters. That's p plus 1 means here p is 1, so that means beta naught and beta 1. So this is a linear model. Maybe these data, these are the data points, and you can represent this one by this blue line. So you have to estimate beta naught and beta 1 hat. Definitely this is the estimated value, and then this is the estimated or predictor, or the the predicted output. So, and sometimes maybe how about this one is, if we just little bit modify let's say this approximation for the same data, let's say beta 1 beta naught hat and the beta 1 x, and just we take another just this one, that beta naught x square. So this is also a linear model, but little bit we need to some sort of mathematical transformation. So this is called quadratic model. But you see, this is a better fit, right? It's slightly better compared to this perfectly this linear model. This is also linear model, but quadratic model. Now see, this one is a two-dimensional example. Again, you see the seniority, years of education and income. And this is basically simulated data. So the blue surface is basically showing you the true function for which this data is basically simulated with some errors, right? Now we can see that errors are not big. You see this little line, maybe this little line represent the error, okay? Okay, so we can write the income as a function of education and seniority. So, and with definitely some error terms. And blue is, let's say, the blue line is the true function, but here just in simulated, this is the, let's say, observation or simulated data, right? This is the red one. And as we said, that income is generally a function of education and seniority. In this case, seniority and years of education. So how we can actually, let's say this is our data. So this red point is our actually data that we simulated from this true function by just adding some little bit error, right? So this one, you see this plane, this is basically a if we think about like that one, this plane is basically coming from a linear model. So linear regression model that fit to the simulated data is maybe like this one, that you just have a parameter beta naught and then parameter b1 multiplied by education level, and then parameter b2 and then multiplied by seniority level. So this is somehow, you see, it is not a very good fit. It doesn't represent every data nicely, but somehow it is a good fit, right? But definitely there are many errors. But how about if we consider this kind of fit, this YOLO surface. See, this is a more flexible regression model that really exactly fit the simulated data much more better. Not exactly, not for every data. Is still little line segment, little error is there, but it is somehow more flexible. Now flexible in a sense that the models that can fit many different possible functional forms for F. So that's some sort of flexibility. So, and we can control the roughness of this fit, that how much we will feed the data. For example, see that this is and by the way, this is we use some techniques called thin plate spline techniques. We will see that how that thin plate spline techniques come up with a very flexible surface so that it fits our data based on our desired level of fitness. So this is a more flexible spline regression model. You see, this exactly for every data it fitted this yellow line. The blue is our true, and this our simulated data, but this yellow, that is basically our model now. So this is exactly fit, but see, there is no error, but we want some error. This sorts of situation actually called overfitting, that for this known data it is working good, but maybe for unknown data it might not work because our model is too much overfitting. So generally we need, so linear model is basically, easy to interpret, but thin plane splice are not, right? So often, we need to play around some sort of trade-off, that is prediction accuracy versus interpretability. If we want accuracy more, then maybe we need to go some more, non-interpretable method, right? On the other hand, linear model is more interpretable, but the accuracy might not be, better. Then, as I said, that sometimes you need to fit the good fit or overfit or underfit. For example, in this situation, maybe this one is okay, it has some error, and we did some flexibility, but this one is overfitting, right? Every data fitting, but this one is underfitting. So this is underfitting, this is overfitting, so this is maybe in between. So thin plate is spline with some degrees of flexible surface working better. So we'll try to understand these sorts of methods. Then there is a schematic diagram lastly, that you see that in this sides we are plotting flexibility, and this is interpretability. So least square method that we saw right now, this linear regression, this somehow here it has this sorts of flexibility, but it is have very good interpretability. Now the variation of these methods are, there are some subset selection or lasso method. This is not flexible, very rigid. Actually least square is also not flexible, because it's almost a parametric, and parameter beta naught beta 1 is very determined, right? But then we can further increase the rigidness and reduce the flexibility. We can reduce some dimension, and then we come up with some subset selection and lasso method. So those are basically less flexible, but it has better interpretability. We can interpret better. Then the little bit, if you go in this side, you can increase the flexibility by so generalized additive models. So generalized additive models is also linear model, but some sort of non-linearity we can handle there. So the flexibility increase, but then you just lose some interpretation ability. Then you have some other method like boosting, pegging, support vector machine, deep learning. Those are actually really not, very, very flexible, because so many of the functions can take so many forms, and it is possible, but then it is very hard to interpret. Now in statistical learning, we try to make a balance between interpretability and flexibility. In machine learning, maybe sometimes we don't care the flexibility, we just try to increase the accuracy, and we go for whatever it is. So that's why in machine learning domain, maybe deep learning, support vector machine, those are okay. But when you come the inference, that how is variables playing role over your output variable, at that time we need to have some sort of idea of inferencing, so we need interpretability also. So then we need to have some sort of modeling accuracy. Okay, so in the next week we will start from here. So this is somehow don't be puzzled, and don't feel its difficulty. This is an overview something, and we will go slowly and gradually from the next week. Okay, so this is an overview, so that's why many things are not known to you. So then see you in the next week.